Hello, everybody. I wanted to explain a little bit the connection between the sparsity-promoting L1 norm and neighborly polytopes. So this is based off some work by David Donahoe and his collaborators and contemporaries, including his co-author Tanner. So I'll briefly review the setup from the last video. Matrix A is a matrix moving us down in dimension. We move from n-dimensional space down to d-dimensional space where d is less than n. And then whenever you write a solution y equals ax, because you have more variables, n, than the number of constraints, d, you expect to have infinitely many solutions. So you can ask for the sparsest solution, the solution x that has the fewest number of non-zero entries. So the L0 norm is just the number of non-zero entries, and we want the fewest non-zero entries. This is a really hard problem in general. It's NP hard. The magic of the sparsity-promoting L1 norm is that instead, you can solve not problem 0, but problem 1, where you minimize the 1 norm of the vector x. And when you do that, in many cases, you can guarantee that the vector x that you found also solves problem 0. And what I mean by many cases is that if x is actually sparse enough, then you can sometimes guarantee that the solution x solves not only problem 1, but also problem 0. This L1 norm is just the sum of the absolute values of the entry of your vector. So if I look at the L1 ball in 2D or 3D, it's this diamond-shaped thing in 2D or this octahedron in 3D. And the typical explanation for why the L1 norm promotes sparsity is that it's spiky. So when you intersect this ball, when you blow up this ball to find your first solution, usually you intersect along a low dimensional face, like a vertex, or here in this picture, you would intersect along an edge probably. And if you hit a low dimensional face of this ball, then you have few non-zero entries, right? So a vertex has one vertex and it has one non-zero entry. An edge has two vertices and has two non-zero entries. And then in higher dimensions, if you have the L1 ball in 10D space, hitting a two-dimensional face would be quite a sparse solution because it has a two-dimensional face has three vertices. So you'd have at most three non-zero entries in your vector, even though in 10-dimensional space, in general, vector x could have 10 non-zero entries. All right, so remember that already. The dimension of a face of this particular polytope is sort of encoding the sparsity of the vector. The number of vertices in that face tell you the sparsity of any vector inside that face. So this two-dimensional face has three vertices, and any point inside that triangle has three non-zero entries, whereas this edge has two vertices, and any point inside that edge has at most two non-zero entries. All right. So this is a probabilistic statement. The overwhelming majority of matrices that map us from n dimensions down to d dimensions, so long as n is large enough and d is no more than 7/10 of n, so we're reducing dimension by at least 30%. The overwhelming majority of such matrices have the property that that if x is a solution to the L0 norm problem with few enough non-zero entries, then x is also the unique solution to the L1 problem. So you just use linear programming, solve the L1 problem, and aha, you found a solution to the L0 problem if there's few enough non-zeros. I call this a corollary. It's a corollary of a result about polytopes. And that's the main connection I want to explain right now is why sparsity has anything to do with polytopes. So the main theorem that gives this corollary is we're going to take our cross polytope in n-dimensional space. Okay, so that's Cn, and we're going to apply matrix A to it to map our n-dimensional polytope down to d-dimensional space. And then the number of faces that you have in that projected polytope tells you things about how likely matrix A is to satisfy this corollary. All right. So here I've drawn C2, our cross polytope in 2D, and C3, our cross polytope in 3D. More generally, let Cn be our cross polytope, or L1 ball of radius 1 in n-dimensional space. ACN is just the polytope we obtained by multiplying by matrix A. So let me quickly get to a picture. Let's choose a 2x3 matrix, maps from 3D down to 2D. So here on the left, I have 3D, and my 3D cross polytope, when I multiply down and map down into 2D space, it just hits this octahedron. So E1 mapped here, E2 mapped here, E3 mapped here, and the 6 vertices of my cross polytope in 3D mapped down, it turns out in this example, to the 6 vertices of a regular hexagon in 2D. Right. What we're going to pay attention to is how many of the faces were preserved. So certainly I've destroyed many of the triangles, but I have preserved all of the vertices, right? So I had 6 vertices before I mapped down, and I still have 6 vertices after I mapped down. That's not always the case. You can find different projections. Say you just projected to the x1, x2 plane, where you project down, and instead you just get a square or a diamond, okay? You wouldn't be preserving all of the vertices if you map down to a diamond, okay? But if you map down to a hexagon, which still has 6 vertices, then you're preserving all the vertices. It turns out that these cross polytopes are spiky enough that when you do these random matrix maps down to lower dimensions, you often preserve many, if not all, of the low dimensional faces. So here we've preserved all of the vertices going from 3D to 2D. If instead you're going from 100 dimensions down to 10 dimensions, you're likely to preserve not only all of the vertices, but also all of the edges and 2-dimensional faces and 3-dimensional faces, for a certain number of low dimensional faces. In this example here, we do not preserve all of the edges. So this edge between E1 and E2 is preserved, but this edge between E1 and E3 is not preserved. It gets buried inside this hexagon. Okay. Great. So my next task is to define K neighborly for you so that I can precisely describe this theorem. To do that, I first need to talk about centrally symmetric polytopes. A centrally symmetric polytope is just one that's equal to its reflection through the origin. So it's symmetric about the origin. So cross polytopes are always centrally symmetric. If you reflect them through the origin, you get the same thing back. And for any matrix A, if you multiply your cross polytope by matrix A, the result is also centrally symmetric. Okay. So what does it mean for a centrally symmetric polytope to be K neighborly? K neighborly means you have as many k-dimensional faces as possible. Okay. A k-dimensional face has k plus 1 vertices. So a two-dimensional face and edge, a one-dimensional face and edge has 2 vertices. And a two-dimensional face, a triangle, has 3 vertices. So precisely, a centrally symmetric polytope is k-neighborly if any collection of k plus 1 vertices, any collection of vertices that could form a face of dimension k indeed do. You can't form a face if you have antipodal vertices, right? Because then that face would pass to the origin, and that's not on the boundary of this polytope. So we never look for faces that contain antipodal points in centrally symmetric polytopes. So we're only going to say that any collection of k vertices, no two of which are antipodal, have to form a face. All right, let's do some examples. This polytope on the right is 0 neighborly. Every vertex is a face. Every collection of one vertex gives a face. It is not 1 neighborly, because here are 2 vertices which are not antipodal, and the edge between them is not a face of this polytope. It's not on the boundary. This cross polytope on the left, this is in fact 2 neighborly. So any collection of up to 3 vertices, so long as no 2 of them are antipodal, indeed form a 2-dimensional face. The cross polytope in dimension n is always n minus 1 neighborly. It has as many n minus 1 dimensional faces as possible, keeping in mind this antipodal restriction. All right, so now we can look at our main theorem a little bit more. The second bullet point is saying, when does matrix A have this problem that's solving the L1 norm problem and also solves the L0 norm problem? Okay, so if you have a solution to the L0 norm problem and it has few enough zeros, then it's also found by solving the L1 norm problem. Okay. So those are the nice matrices. Those are the overwhelming majority of matrices that allow us to solve sparsity problems using the L1 norm approximation. So being one of these nice matrices actually turns out as having the property that when you multiply your cross polytope by this matrix, you preserve all of the vertices of the cross polytope, and you preserve faces up to dimension k. Okay, you preserve all of the faces up to dimension k. Right. So in this picture, we only preserve the faces up to dimension 0, the vertices. Okay, so that means that we only have these nice sparsity promoting properties when our sparse solution has at most 1 non-zero entry. But if we preserved all the faces up to dimension 7, right, then we would have these nice sparsity promoting properties. L1 norm solves the L0 norm problem for all sparse solutions that have up to at most 7 plus 1 or 8 non-zeros.